Okay, maybe we'll start a minute or two earlier so that I won't take up too much of the speaker's time. Yes, you will hear me very loud. Don't worry, Manny. Okay, good morning, everyone. Welcome to this track 1 session, which is on paleoclimatology. Of course, the subject is very diverse, and we have a range of excellent speakers. We have Tom Segalstad, who will be the first speaker this morning. Each speaker has been told to give about 20 minutes of talk so that there will be ample time for questions and discussion, which is about 10 minutes. So everyone are allotted 30 minutes. So when you hit the 30 minutes limit, I will be here to make sure that this procedure is properly followed. So without further ado, let me first introduce the first speaker of this morning, which is Professor Tom Segalstad from University of Oslo. I guess I do not want to take up too much time describing all his work, which is all inside the brochure that you receive. Tom, of course, is a geochemist who's been studying this issue for a long time. And the topic of his talk this morning will be on carbon isotope mass balance modeling of atmospheric versus oceanic CO2. Okay, Tom, please.
Thank you, Willie. Good morning, ladies and gentlemen. I hope that you're all awake. During my talk, I guess most of you will fall asleep. Let me announce that there will be a second talk, and it should be right here. High scores for ice cores. Are ice cores really a climate archive? Session 3 right here, track 1, third talk at 3:25 today. So we will look at the natural inorganic carbon cycle based on geochemistry and carbon isotopes. This is what we will talk about. And if you're a scientist, you can read the text here. If you don't know what I'm talking about, you can listen to me. So we'll try to explain in simple terms. Okay. The Intergovernmental Panel on Climate Change, IPCC, asserts that the burning of fossil fuel makes this anthropogenic CO2 accumulate in the Earth's atmosphere because this CO2 has a long lifetime, up to 200 years. And this assertion will here be tested with carbon isotopes. But just remember this curve from the third assessment report. Calendar is the modern father of the tenet that there is proof of increasing level of CO2 in the air and that this will lead to warming of the planet. And we see the shotgun plot of chemical analysis of CO2 for the last 200 years. Here's the value for the analysis, here's the year. From these, Calendar established the following mathematical filter. And he writes, he rejected the values diverging more than 5% from what he believed was correct. No, you shouldn't laugh. This is high science. And everybody could see the resulting rise in the atmospheric CO2. See here? This type of work was followed by studies of air bubbles in ice cores. We'll continue in session 3, assuming these to be representative of earlier atmospheres. The dots and uncertainty bars in black were published in their paper in 1982. You see some high values here, high values here. And then the authors, 6 years later, in another paper in Nature, claimed to present the same data. And now the green is what they presented. And you can now see there's a rise of CO2. But now the high values and the uncertainty is gone, and the data shows a rise towards an important level that had to be defined, the pre-industrial CO2 level in air. Next, it was important to show a rise in CO2 from the pre-industrial level. And only one ice core showed this rise, and that was the Sippel core from Antarctica. But this core partially melted during transport across the equator and should have been discarded. But there was another problem. The curve didn't match in time with the present measurements. So hence the Sippel core data was parallel displaced to fit the data. So now we all see that there is proof of an increasing CO2 in the air, which must be anthropogenic. Now, CO2 measurements near the top of the strongly CO2 emitting active volcano Mauna Loa in Hawaii have been taken as representative of the world's air CO2 level. But there is a 50% error versus the expected CO2 level from burning fossil fuel. If you start the two curves right here when they start the measurements of Mauna Loa, we see that the fossil fuel rises double amount versus the calculated gigatons of carbon from Mauna Loa that is representative. And this enormous error of 3 to 4 gigatons of carbon annually has been nicknamed the missing sink, and disproves the IPCC. Now, this diagram shows the anthropogenic emissions of CO2 from burning of fossil fuels. Here's the cumulative, here's the annual, and what we should expect now is that the measurements should measure exactly the same as we see in the cumulative emissions. But we don't see this. Because if all anthropogenic CO2 is accumulated in the air, with a long lifetime, the air CO2 level should increase just like the accumulated CO2 emissions, and that is not seen. Now we will turn to the main topic about this talk, that is carbon isotopes. And we see that carbon isotopes give us the only way to inequivocally determine the fraction of CO2 in the atmosphere. We see a CO2 molecule here, and it has a carbon-12 isotope between the two oxygen atoms, and here we see a carbon-13 together with two oxygens. So then we measure the ratio between the carbon-13 and the carbon-12, and we express that in a delta value, delta notation, that is given below here. So the delta notation gives you then the ratio of the carbon-13 versus carbon-12. So now, this is the main thing I will show you today. Here is this delta value, and here is the value of the atmosphere at -7, the value of the CO2 dissolved in the ocean at 0, and limestone here at about +3. And all these three reservoirs are in equilibrium. And we can see this empirically by experiments and atomic physics calculations. Now, burning of biospheric fossil fuel, which has a value down here at about -26, will represent then 100% in a mixing with the atmospheric CO2, all natural, right here. So we have a 0 to 100% mixing scale over here to your right. And then the question is now, what is the value of the CO2? If we take the 1988 value, we will see that the 98 value of the carbon isotopes point out that 4% only of the anthropogenic CO2 is in the air. Not the 21% that is expected from IPCC if CO2 has a long lifetime in the atmosphere. So the expectance by IPCC is not consistent with the measurements. So I could have stopped here and you all could go home because this is the main thing I want to tell you. But we can go a little bit further. Why did I take the numbers from 1988? If you look at the carbon isotopes presented by Keeling and others, we will see that they have introduced a correction in the numbers. And I find that very strange. If there is a systematic error, why is not the whole sequence of numbers corrected? So that's why I have stopped at 1988, where I've used the data that IPCC basically using, and we'll keep it at 1988. I don't want to dig into the trouble over here. And what has the carbon isotopes to do with climate? Now, if you use the values from Ramanathan and co-workers, we see that more than 1 kilowatt of energy is received from the sun per meter square, and some of this is held back in the atmosphere. 146 watts per square meters is held back, and that is a natural greenhouse effect. And this is what we need in order to have a temperature of about +15, an average temperature, versus -18 if we didn't have the greenhouse effect from the atmosphere. But 98% is dominated by water vapor. And anthropogenic CO2 then must be less than half a watt per square meters, less than 0.1% of the greenhouse effect, judged from the amount of anthropogenic CO2 that we find from the carbon isotopes. But clouds are the real thermostat, and they are able to regulate the temperature much further than the CO2. Now, what we can do next is we can do a so-called isotope mass balance calculation. And what we do is say that the total carbon delta value for the isotopes equals the sum of the products of each delta value for the reservoirs times the mole fraction of the different reservoirs. So then we can say, okay, we have an X, we have a Y, we have a Z, and we take the isotope values for the three different reservoirs, and we calculate the delta value, the total delta value for these, and we find out if they match the amount of total carbon in the atmosphere, which is 748 gigatons of carbon, which should have the measured isotopic value right here. We see for some lifetimes on the logarithmic scale here, if we sum this, we see that there is a missing part of the carbon because the atmosphere will be too light. Here it will be too heavy. And where the two lines cross, we find the correct lifetime of the CO2 in the atmosphere, which comes out to about 5 years. So this is what we can do. And this confirms the maximum 4% of the atmosphere is with this component, the fossil fuel component. 96% is indistinguishable from non-fossil fuel sources. And 134 gigatons of carbon, that is 18% of the air CO2, is exchanged each year, far more than the 7 gigatons of carbon annually released from fossil fuel burning. And we also see why the IPCC's rough indication lifetime, 50 to 200 years, for atmospheric CO2 gives an atmosphere which is too light, only 50% of the total mass. Now we see the artificial 50% error in their model, the missing sink. Now, does this match other people's work? Well, we can determine the lifetime with radioactive, radiogenic, and stable isotopes, and we see a number of other measurements showing lifetimes of about 5 to 6 years, not the 50 to 200 years of IPCC. If you look at Rhoda's figure here, he says that for the top 50 meters of the ocean, the lifetime of CO2 is 10 hours. Upper kilometer of the atmosphere, so bottom kilometer of the atmosphere, the lifetime is about 1 hour. And you can see down to 1 kilometer's depth in the ocean, the lifetime of CO2 is just 2 or 3 years. And also mind you that the upper 200 meters has enough calcium to bind all remaining fossil fuel CO2 as calcium carbonate. So what's the fuss about? Now, IPCC considers the ocean clean distilled water. CO2 enters the atmosphere from many sources to the left here, and CO2 from the air dissolves into bicarbonate and precipitates with calcium to calcium carbonates, also used by organisms to make their lime shells. This is analogous to breathe CO2 down in a test tube with calcium ions, where calcium carbonate precipitates almost instantly. You can do that at home, and I made another little video here that's created quite a bit of fuss on, how can I get the cursor? Here comes the cursor. We'll see if this experiment will load. If not, you can see it on YouTube. And I got a number of nasty emails saying that CO2 is not dissolving in water. Okay, I pressed too many times here. Slow. Now, what have we got here? The video shows that a candle floating in the water, burning in the air inside the glass, converts the oxygen in the air to CO2. The water rises in the glass because CO2, which replaced the oxygen, quickly dissolves in the water. And the water contains calcium ions because we initially dissolved calcium hydroxide in the water, and the CO2 produced during oxygen burning reacts with calcium ions to produce solid calcium carbonate, which we can see is whitening the water here when you turn on a flashlight. And this little kitchen experiment demonstrates the inorganic carbon cycle in nature. The oceans take out our anthropogenic CO2 gas by quickly dissolving it as bicarbonate ions, which in turn forms solid calcium carbonate, either organically in calcareous organisms or precipitates inorganically. and the calcium carbonate is precipitating and not dissolving during this process. We also see that CO2 reacts very fast with the water, contrary to the claim by the IPCC that it takes 50 to 200 years for this to happen. So you can go home and try this for yourself in your kitchen sink. If I can play that again, I don't have the time, so you have to come back later and see that. Sorry about that. Willie is very tough on me here. You can go on YouTube, or you can go to my website and run it as many times as you like. Now, what about volcanism? Michael Bodico has shown a very good correlation between emissions of CO2 through periods of extensive volcanism, as we see with the lines here, and CO2 emissions. And at the same time, he had showed deposition of calcium carbonate in the sea. Here are the two curves put together in another publication by Bodico. And this has happened during the Earth's last 600 million years. Here you see one of the bigger producers of CO2, the carbonate volcano Aldingo de Lengai in East Africa. A mantle melt may have up to 8% CO2 at 125 kilometers depth. And surface lava can only hold 0.01 to 0.001 weight% CO2 dissolved. The difference is degassed to the atmosphere. And here you see a picture from a master thesis work, immiscible magma carbonate in nephelinite. And you can see large amount of CO2 will be emitted during eruption because this is now frozen CO2 in a way in the magmatic calcium carbonate. So when the lava erupts, you will have decompression, the CO2 bubbles come out, and there will be vast amounts of CO2 coming out. And now, IPCC uses Gerlach's earlier papers saying that there is very little CO2 coming out, but now, if you look at his later papers, he's saying that we find now by measuring several times larger than previous estimates. So every time they measure now, they measure much more than they found before. Here is a diagram by my colleague Phil Kyle, which shows the fairly large amounts of CO2 coming out from different volcanoes. And by making some estimates, we may see that there is a chance that the volcanoes emit more CO2 than the anthropogenic amount. But isn't this strange? Even if IPCC asserts that only a slight CO2 will dissolve in the ocean, this minute amount of CO2 will make a catastrophe by dissolving all calcium carbonate in the sea. And this assertion can be tested by data and thermodynamics, something that was not done in the UN-supported second symposium on the ocean in a high CO2 world. You'll get to hear something I didn't hear at this conference. Now, a little bit of chemistry. First of all, you have the CO2 gas in the atmosphere, which dissolves in the ocean. That's what we call dissolution. It reacts with water to form the carbonic acid by hydrolysis. Then it protolyzes, making one proton and the bicarbonate ion. And the bicarbonate may protolyze again, and giving the CO3 2-. And the calcium ions may combine with the CO3, ions, and produce a solid calcium carbonate precipitation. And then, of course, we have protolysis of the sea, water, 2 H pluses and 2 OH minuses to 2 waters. And it all sums up to that the CO2 air plus the calcium ions plus bicarbonate makes calcium carbonate solid, the stable phase, plus water. Now, for the acidification thing, remember now that you have much more OH minus in the sea that you can ever produce by the protolysis of the carbonic acid. So just ask back now, how much OH minus do you have in the sea to neutralize the acid? So the increase in CO2 will force the reaction to the right, according to the law of mass action and Henry's law. And what is Henry's law? Well, Henry's law constant is an equilibrium partition coefficient for CO2 in air versus CO2 in water. And it is about 1 to 50 at 25 degrees C. So at lower temperature, you can have more CO2 dissolved in the water. And we have all experienced this. Cold soda or beer or champagne can contain more CO2 that has more effervescence than hot drinks. We don't like hot beer. So So the brewery said they add 3 liters of CO2 to 1 liter of water in the soda. Where did all the CO2 go? Well, it is dissolved in the water. The soda bottle is a good analog to nature. 50 times more CO2 is in the ocean than in the Earth's atmosphere. Now they claim that a drop of 0.1 pH units is showing that we are making acid of the seawater. What are the natural numbers? We see here from Western Pacific from pH 7.8 to 8.5. And we see that at higher or lower latitudes, you have lower, because of the change in proteolysis of seawater with temperature, you have lower natural pH. Imagine now if you get some cold water upflow here, then of course you will measure lower values. But this has nothing to do with the anthropogenic CO2. The ocean's carbonate system will act as a pH buffer, and we can calculate the pH, and we can then calculate what is the stability field of calcium carbonate in the sea. Here's the seawater, here's the pH, here's the amount of CO2 in water. Can you increase the CO2 in water and get out of this field of solid calcium carbonate? No, you cannot. You increase and you cannot get out of the field. The only thing you would be able to do would be to increase the H plus 100 times. You get 2 pH units lower, then you can dissolve it. But then you will require 100 times the CO2 concentration in the air. And there are more buffers. The anthracite feldspar kaolinite buffer has a 1,000 times larger buffer factor than the ocean's carbonate buffer. You have clay mineral buffers, calcium silicate, calcium carbonate buffers, and all these buffers act as a security net under the major buffer. They add up to an almost infinite buffer capacity, quote unquote, by Stam and Morgan in their authoritative textbook, Aquatic Chemistry. And Brian Mason says the ocean may thereby act as a self-balancing mechanism in which most of the elements have reached an equilibrium concentration. And we see this through a considerable constancy of sedimentation over the last 100 million years. And I just put out a clipping from his book. To double the departure pressure of carbon dioxide in the atmosphere would require the addition of much more than is now present therein, because most of that added will be absorbed by the ocean. The oceans, by controlling the amount of atmospheric CO2, play a vital part in maintaining stable conditions for organic life on the Earth. The spectacular facts are hard to beat. Of course, here you see the positive proof of global warming. And a picture of pretty bleak, gentlemen. The world's climates are changing, the mammals are taking over. We all have a brain about the size of a walnut, especially this speaker, my opponents say.